So this section I know has a really weird title with chapter 2 extension, all that stuff. Don't worry about this. It really goes hand in hand with what we were talking about with the rational and irrational numbers. It had, we're going to talk about infinity, and it really stems from those ideas in section 6.4, so they go hand in hand no matter what the crazy title says. Now, at this point, you guys kind of know I'm a little bit of a math nerd. This topic is something that I really love, so sorry if I get a little geeky on these things. They just make me pretty excited. So we've got to get a few definitions down. The cardinal number of the set is really simple. It's the number of items that are in a set. And I've got some examples down here. So if you look at the example, one here, the cardinal number is just 3. There are 3 items in that set. And you could technically have anything be in a set. The people in our class could be a set of things. So here in the third example here, those are just symbols instead of numbers. And if we count this up, there's 1, 2, 3, 4, 5. So that cardinal number is 5. While I'm doing it, I'll go ahead and do example 2 here. We've got that ellipse that we've seen come up a couple of times. That ellipse in the middle there means everything in between. It's basically a way of saying, hey, I was lazy and didn't want to write out all those numbers. So this includes all the numbers that might appear between 20 and 55. And this is a pattern. It looks like we're counting by 5s. So you're more than welcome to just kind of count on your fingers. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55. And that is 11. It's nice looking 11 there for those cardinal numbers. Now, one time that sets are really important, these cardinal numbers come up, are when 2 sets are equivalent if their cardinal numbers are equal. So to be equivalent doesn't mean that you have to be the exact same thing. It just means that you have the same cardinal number. So you could have different items in your set. As long as you have the same amount of items, you are equivalent. And we use this equivalent to set up what's called a one-to-one correspondence. So one-to-one correspondence is when we're going to compare 2 sets and they have the same cardinality, so they have the same number of items. So to do this, we basically are going to pair an item to each other, and that's what I have in this last one. We're going to set them up as a pairing, and this compares the size of the 2 sets. This is actually how we start teaching children to count. If you think back to maybe, I don't know if you remember when you were this little, if you've ever been around a small child, we teach them to count by maybe putting like one item in their hand, maybe a goldfish. My parents used M&Ms, a block, and we say 1 and then 2. So we're pairing a word with an item, and that's a one-to-one correspondence. We'll do some that aren't as abstract down here. So I will pair 5 to the number symbol, 10 to the dollar symbol, and 15 to the percent symbol. You do not have to go in order, but that honestly, we're going to get to some that are a little trickier, and it's just a lot easier to go in order. There's nothing saying you have to, but it's going to make our lives a lot easier if you do. So I would encourage you to go in order. So these guys do have a one-to-one correspondence because every number can go with a symbol. Let's look at one that doesn't work. So I compare the number 2 with that hashtag symbol or pound sign or number symbol, the number 4 with the dollar symbol, the number 6 with the percent symbol, and then the number 8 doesn't have anything to go with. So we say that this does not have a one-to-one correspondence. That first set of those the numbers is larger than the second set of just the symbols, is how we would read that.